Hey y'all, welcome to the Thermochemistry OWL review. We're just going to walk through most of the different groups on the OWLs. I think this OWLs is a pretty straightforward one, but definitely practice with certain problem types of these. And I would say especially applying stoichiometry to all of these different groups is going to give you a good grasp of where you need to be for some of the calculation-based portions of this unit. So group one is an interesting group in that it focuses solely on work and energy as a product of both heat and work, and revolves around this formula where the change in energy is equal to heat released as, or energy released as heat and energy released as work, or absorbed as work, anything like that. And so one of the practice problems we have gives us a chemical reaction is run in which 614 joules of heat are absorbed and the internal energy changes by positive 893 joules. So basically what we need to do is just figure out which ones of these numbers represent our variables. So positive 893 is going to represent our delta E, our total change in internal energy. 614 being absorbed, that means it's positive, it's going into the system, is going to represent our Q because it's heat. And so W is going to be our unknown, and we can kind of understand that when we look at what the problem's asking us to do, calculating work. So 893 equals 614 plus W. That means W must equal 279 joules. All of the problems in this group are just some iteration of solving for either delta E, Q, or W. Pretty straightforward. Group two, we get into definitely a little bit more complicated of a group, and I would argue probably the most important group because we're working with calculations using stoichiometry. So in this question, we have a thermochemical reaction for calcium carbonate to form calcium oxide and carbon dioxide. And we're asked how many grams of calcium carbonate would be made to react if 49.3 kilojoules of energy were produced. And we're given a balanced chemical equation with an enthalpy change there. And so where I want to start is always with my one number that I have, which in this case is 49.3 kilojoules of energy. That was how much was provided. And so if I set that over 1 and start some stoichiometry, well, then I look for another conversion I have that 178 kilojoules of energy are present every time 1 mole of our substance reacts. And we are looking for how many grams we have, so we want to multiply by the molar mass of calcium carbonate, which is about 100 grams, conveniently enough. And we get that it would take about 27.7 grams of calcium carbonate to produce that much energy, that 49.3 kilojoules of energy. And we can use this by using the heat of formation that we're given, or the enthalpy there, because that's basically in kilojoules per mole, no matter what, even if it's not necessarily stated like it's not in this one. Okay. Another problem in group 2 that we could look at is a little bit of an expansion on that. We have a thermochemical equation this time that is a combustion reaction, and we have 9.94 grams of our reactant, and we have plenty of O2, and we're asked how much energy is there, and is that energy released, or is it absorbed, or released? In the OWLs, they say evolved instead of released for whatever reason, but we can just say released. So in this one, again, we want to start with the number we have, 9.94 grams of our reactant. And we divide by the molar mass this time, which is about 30 grams per 1 mole. And then we can use that number that we're given. 1 mole gives off 563 kilojoules of heat. This tells us that our answer is negative 187 kilojoules. In other words, 187 kilojoules are evolved or released. I don't really care which of these you use. I definitely used released more, but the owls seem to use evolved. So just know that they're interchangeable when you're working through this kind of work, and pay attention to the signs given in your heats of reaction or enthalpies of reaction. And then another one with the stoichiometry, we're going through quite a bit of these because, like I said, they're quite important. We have a thermochemical reaction of nitrogen monoxide and oxygen to form nitrogen dioxide. And we're asked how many grams of nitrogen monoxide would have to react to produce 18.4 kilojoules of energy. So we always want to start with that number we have, 18.4 kilojoules, and then see where we can go from there. Well, we know that 114 kilojoules are given off. Interestingly, not when 1 mole of nitrogen monoxide reacts, but when 2 moles of nitrogen monoxide react, because there's a little 2 in front of it's our stoichiometric coefficient there. So 2 moles of nitrogen monoxide. And then we can multiply by the molar mass. 1 mole of nitrogen monoxide is about 30 grams. And so we end up that 9.68 grams of nitrogen monoxide would be needed to react to produce that much energy. This is important because even though this may be in kilojoules per mole, we have 2 moles there, which is different from like a problem like this where we only have 1 mole, or even a problem like this where we have 1 mole that we're working with. So make sure you pay careful attention and notice that this has a coefficient of 2 as you're working through this problem, or any problem like this. Pay attention to your coefficients because they're relevant. Okay, so our stoichiometry group, very important, but it's not the only important one. Another important one is our calculations with specific heat. Again, the owls choose to define specific heat a little bit differently. They represent it with the letter S. We usually represent it with the letter C, and that means we usually use the formula Q equals MC delta T, whereas they use the formula Q equals SM delta T. Both are the same thing. These two are equal to one another. Use what you're more comfortable with. I'm definitely guessing that you're more comfortable with MC delta T because that's what you did in first year chem. But anyways, we're given this problem where we have a student who finds that it takes 31.4 joules to increase the temperature of 10.8 grams of solid lead from 20.1 degrees to 39.6 degrees Celsius. The specific heat of lead calculated from her data must be blank. So let's just start plugging in numbers. 31.4 in this case is Q. It's our total heat of reaction. Our mass is 10.8 grams of lead. We're solving for C. And our temperature change from 20.1 to 39.6 is positive 19.5 degrees Celsius. So we can put our little multiplication signs in there. And then if we solve for C by doing that, we get that C equals 0.149 joules per gram degree Celsius. Now, it's worth noting that the actual specific heat of solid lead is about 0.159, but this is pretty impressive for experimental data in this student. But it is worth noting if we work with solid lead in another group, we'll have to use the actual specific heat of solid lead and not this experimentally calculated one, which we're about to do in a second. In group 4, we're basically calculating Q when we're given specific heat. So again, very similar to these other types of problems in group 3, except this time we are solving for Q. So this time we're asked what is the energy change, or what is Q when temperature of 14.6 grams of solid lead is decreased from 35.1 to 23.3 degrees Celsius. So this time our Q is going to equal 14.6 grams times the specific heat of solid lead, which, like I said, is 0.159, even though we just calculated it to be 0.149, times delta T, the temperature change, which in this case is negative 11.8. Pay attention to the fact that our temperature is decreasing not increasing here. That means our Q is ultimately going to be negative 27.4 joules. So that sign, that negative sign, very important here. We can tell that this must have a negative energy change because our temperature is decreasing. That should hopefully make sense intuitively to us. And then moving on to group 5, a little bit more work with specific heat, I would say. We have a sample of solid lead, our favorite substance again, that's heated with an electrical coil. We have 27.4 joules of energy being added to a 14.6 gram sample, and the final temperature is 35.1 degrees Celsius. What is the initial temperature of the lead? So this one is a little bit different because initial temperature is not in our Q equals MC delta T formula. So we have to first solve for one of those variables and then go from there. The one that's helpful is obviously delta T. So if I plug in 27.4 for Q, 14.6 for M, 0.159 for C, and then I solve for delta T, I get that delta T is positive 11.8 degrees Celsius. Hopefully that makes sense. We add energy, we add 27.4 joules of energy, so the temperature of our system increases. Now, if I've added energy to something and the final temperature is 35.1, that means my initial temperature is going to be 35.1 minus 11.8. That means my initial temperature is going to be 23.3 degrees Celsius. So we can kind of make sure that we have our answer right by making sure that it makes sense with what we know about chemistry. If I add in energy, it makes sense that my initial temperature would increase to be my final given temperature. So even though you're not solving for something directly in our Q equals MC delta T formula, hopefully it's still easy enough to figure out what our initial temperature is. You could also just use your delta T, substitute in T final minus T initial for delta T if you don't want to have to break it into two equations. That's totally fine as well. In group 6, we get into calorimetry, another important concept, one that we talk a lot about in first year chem, as we talk about how calorimeters are kind of these perfect objects that absorb no heat. And then we expand on that in this class by taking into account the fact that calorimeters do actually absorb a little heat. And we'll talk about that more in the next group, like we talked about it in the lab. So in this one, we have an electric range burner that weighs 672 grams. We turn it off after it reaches a really high temperature of 458.2 degrees Celsius, and it cools to 22.2 degrees Celsius. We're asked to calculate the specific heat of the burner if all of the heat evolved or released from the burner is used to heat 555 grams of water from 22.2 degrees Celsius to 81.1. So basically, as our burner is cooling, it's heating up some water. So what we need to do is we need to say that the heat gained by water is equal to the heat lost by our burner, and solve for the heat gained by water first. This is easy because the specific heat of water is a known value, 4.184 joules per gram degree Celsius. This is definitely something that is helpful to memorize if you don't already have it memorized. So we have 555 grams of water. Our specific heat of water is 4.184. And the temperature change of water, it increases from 22.2 to 81.1 degrees Celsius. So that's an increase of 58.9 degrees Celsius. That means the heat gained by water is about 137,000 joules. Now, if we remember this kind of rule that we have to follow during calorimetry, we can set this equal to our heat lost by the burner and say 137,000 is equal to our mass of burner, 672, times our specific heat of burner, times the temperature change for it, which is 436 degrees Celsius. Now, if you want to be specific and say negative 137,000 and negative 436, that's totally fine. But sometimes working with negatives is weird, so I usually just keep things in the positive world when I'm working with calorimetry, unless I'm asked to solve for what the temperature change is and I want to be specific. But if I plug all those numbers into my calculator, I get that the specific heat of my burner is 0.468 joules per gram degree Celsius. This is another point where I would say I check myself against chemistry knowledge. I'm assuming that a burner is probably going to be made out of metal, so it's going to have a relatively low specific heat. It's about 10 times lower than the specific heat of water, so that makes sense to me that it's about 0.468. That's obviously an imperfect system. You might have a made-up metal that has a really high specific heat, but generally I think you'll find that College Board and our tests try to keep metals with low specific heats, at least lower than water, which has a pretty high specific heat. Another type of calorimetry problem you could see is with like a coffee cup calorimeter or like a styrofoam calorimeter, where you are only measuring a change in water and a change in something that is put in water rather than a range burner. It's essentially accomplished the same way, in which we need to solve for the heat gained by water at first. So in this problem, we have 77.1 grams of water, which has a specific heat of, again, 4.184 joules per gram degree Celsius, and it heats up the water 2.16 degrees Celsius. That means our heat gained by water is equal to 697 joules. One big thing that we need to keep in mind here is that our final temperature is going to be a temperature of the system. It's an equilibrium temperature. That means not only is the water that temperature, but also the metal that we dropped in is also that temperature. So this final temperature is used to calculate both of our delta T's. Now we set 697 equal to Q lost by metal, and say that our mass of metal is 18.9. Our C is what we're solving for. Our delta T is from that 98.48 that it started at to the 25.9 that the system eventually cools to. And what is that difference? That's 72.58 degrees Celsius. That means C is going to be equal to 0.508 joules per gram degree Celsius. Again, this makes sense to me. It makes sense that a metal is going to have a much lower specific heat than water. So I can plug in my final answer there. Next, we get into some more realistic applications of calorimeters. These calculations that we'll do in Group 7 are super similar to the calculations that we did in our lab, where we're told when a solid dissolves in water, heat may either be released, evolved, or absorbed. And the heat of dissolution can be determined using a coffee cup calorimeter, which is exactly what we did. We dissolved magnesium or magnesium oxide in hydrochloric acid, which, for our purposes is like water. In a lab, a student finds that when you dissolve 0.72 grams of potassium hydroxide in 111.2 grams of water, the temperature of the solution increases from 23.82 to 25.46. So we're seeing an exothermic reaction. That is something that I initially notice heat is being released because our system is increasing in temperature. The heat capacity of the calorimeter, referred to as the calorimeter constant, was separately determined to be 1.65 joules per degree Celsius. So that's worth noting. We don't have to calculate it this time by doing the T average and T mix. We're just given that. Based on the student's observations, calculate the enthalpy of dissolution in kilojoules per mole. This is another important point. We are working our way towards kilojoules per mole, even though a lot of our initial calculations are going to be in joules and grams because we're working with C, which is in, that's not a very good C, which is in joules per gram degree Celsius most of the time. So anyways, we set up this problem just like we set up the problems in the lab, where we say our heat is equal to negative heat of system plus heat of calorimeter. So our heat of system is equal to the mass of the system, so the mass of the water plus the mass of the potassium hydroxide, which is 111.92 grams, times the specific heat, which we're told just to use the specific heat of water, 4.184, times the temperature change, which is our increase, our 1.64 degrees Celsius. So that's our kind of how much heat our system is going to produce. And then we want to figure out the calorimeter, what's going on with that. So our calorimeter constant is 1.65. Our temperature change is again 1.64 degrees Celsius. We don't need to worry about the mass of the calorimeter. The math just doesn't really necessarily care about that. And so we get negative 771 joules. I feel good about this track that I'm on. 771 is in the negatives, which means heat is being released, which makes sense that my system's temperature is increasing. But again, I'm not looking for Q. I'm looking for enthalpy of dissolution in kilojoules per mole. So now what I need to do is I need to convert joules into kilojoules per mole. And what I need to do for that is to figure out how many moles did I work with. Well, I worked with 0.72 grams of potassium hydroxide, which has a molar mass of 56.1 grams per mole. So that means I worked with 0.0128 moles of reactant. So since I have this number, I'll just kind of store this off to the side. I know I have 0.0128 moles. I have negative 771 joules, which means I can say negative 771 joules over 0.0128 moles. This gives me joules per mole, and I can turn joules into kilojoules by dividing by 1,000. And then I get that I have negative 60.2 kilojoules per mole is my enthalpy of dissolution. So these problems are really only as difficult as it is to remember. Let me highlight that formula. As it is to remember this formula. So look back in your lab, definitely. And also something worth noting is we definitely want to make sure we're adding our masses together here. So masses added. We don't want to forget, even though we would get a pretty similar number because relatively speaking, there's a lot less metal than there is water. So make sure you add your masses together. That can be an easy mistake. Next, we get into group 8, which has Hess's law. We're going to skip that because it's just single reaction Hess's law. We're either reversing it or we're keeping it the same. So we're going to, or multiplying it or something. So we're going to skip that to multi-step Hess's law. And we'll look at this problem 1, where we have 2 partial reactions that equal 1 kind of total reaction. So we want to figure out how can we manipulate this to equal the total reaction. So the first thing I always do is just look for something unique. The thing that stands out to me is this nickel oxide, nickel 2 oxide. So that nickel 2 oxide is on the products of reaction 1, and it's in the reactants of reaction 3, and its coefficient has also changed. So I'm going to reverse this reaction to get it on the right side, and I'm also going to divide it by 2 or multiply it by 0.5. So I'll say to this number, I'll divide by negative 2 or multiply by negative 0.5, whatever you want to think about it in. The second reaction, I notice zinc oxide, they're on the product side in both, so I don't have to reverse it, but the coefficients do change, so I need to divide this just by positive 2. Whatever I do to the reactants or to the equation, I also have to do with the enthalpy changes. So my negative 479.4 kilojoules when dividing by negative 2 becomes positive 239.7. When I divide 696.6 by 2, I get negative 348.3. I combine those, and I'm left with a standard enthalpy change of negative 108.6 kilojoules per reaction. Hopefully that's pretty easy for us now. We've worked with Hess's law quite a bit, and we can do much more complicated ones than just the two-step ones our OWLs ask us to do. Don't think that just because you've mastered the two-step ones means you have totally mastered all that Hess's law can throw at you. You maybe want to do some of the two-step or three-step or even four-step ones that are present in that Hess's law practice problems. Finally, getting into the last couple groups, we have group 10, which asks us to use standard heats of formation to calculate enthalpy change. I think these are fairly easy to think about. The only difficulty is that at times people confuse heats of formation and bond energy, and they end up subtracting the wrong thing. So what I like to think about is that heats of formation are calculated when things are formed. And so our products are being formed and our reactants are being broken. And so we want to do products minus reactants because our products are being formed. We want to keep them positive. Our reactants are being broken, so we want to flip whatever those numbers are around. So this time around, we will look at our heats of formation using our data table. So since it's products minus reactants, on the product side, I'm going to put my 4 times the heats of formation of CO2 in its gaseous form, plus 6 times the heat of formation of H2O in its gaseous form. Important to pay attention to those states of matter there. Minus reactions, I have 2 times my heat of formation of C2H6 plus 7 times my heat of formation of O2. Now, if I compare this to my table, I see that the heat of formation of O2 is 0. The heat of formation of C2H6 is negative 84.7. The heat of formation of gaseous water is negative 241.8. And the heat of formation of gaseous carbon dioxide is negative 393.5. None of these are numbers that I need to memorize. I guess it might help that I remember simple forms are 0, but ultimately none of these are things that I need to memorize. I'm going to look at my table of heats of formation, and I get that my final answer is negative 2,855 kilojoules. Again, the important part of these problems is just to remember products minus reactants, and that's because I'm thinking formed is positive, being broken is going to be negative, so I'm subtracting everything that is not forming, which are the reactants, obviously. Group 11, really getting to the end now, or the last few ones. Group 11, we have standard enthalpy change already being measured, and we're asked to calculate the standard enthalpy of formation of H2O. So this is very much working just in the opposite direction of last time. This time we want to set our overall change as negative 776.4, and that's equal to our products minus reactants. So our, let's see, our first product is N2, so that's going to be 0, plus 2 times H2O, which is what we're solving for, minus our reactants, which is 2 times the 90.3 from NO, plus 2 times 0 from H2. We plug this into our calculator. We get that negative 595.8 is equal to 2 H2O. So to figure out for 1 H2O, we divide by 2, get negative 297.9 is equal to the heat of formation or enthalpy of formation of H2O. And that's in kilojoules per mole. Group 12, this should be hopefully a pretty straightforward group, just converting from one form to another. A joule is a SI unit of energy, so the international standard, but sometimes we work in calories or even kilocalories or kilojoules as well. And we're told that 1 calorie is equal to 4.184 joules. And so the first way to do these is the easiest part, and it's just to convert from joules to kilojoules or kilojoules to joules. And to do that, we just need to move our decimal place 3 times. So 643 joules is 0.643 kilojoules. 0.513 kilojoules is 513 joules. Make sure you're moving it in the right way. Think about this logically. A joule isn't going to be bigger than a kilojoule, so your number shouldn't be going up. And then we need to figure out how can we use this 4.184 number. Well, if 1 calorie is 4.184 joules, that means I can divide joules by 4.184 to come up with calories. So 643 divided by 4.184 is 154. 513 divided by 4.184 is, let's see, what is that? 123. And then in this middle chunk, I'm going to multiply by 4.184. So 109 times 4.184 is 456. And then we move our decimal over 0.456. Hopefully that's a very easy group for you. And now lastly, let's see. I just left the answer hanging out there. Let me cross that out, but we kind of know where I'm going. In this problem, we have quite a bit to work with here. Ethanol C2H6O is something that's blended with gasoline. Ethanol has a combustion that releases 326.7 kilocalories of energy per mole. The combustion of another combustible substance, 2-methylheptane, C8H18, releases quite a bit more kilocalories of energy, 1,306 kilocalories of energy per mole. How much energy is released during the complete combustion of 377 grams of 2-methylheptane? So this is just like some stoichiometry. We have 377 grams of our 2-methylheptane. We divide that by its molar mass, which is something like 114 grams per mole. And then we multiply it by its combustion energy, which is 1 mole releases 1306 kilocalories. So in total, if we combusted 377 grams of 2-methylheptane, we would release about 4,310 kilocalories of energy. So that would be our answer that plugs in there. Yeah, I just spoiled the second answer as well again. But anyways, that's what we plug in there. Second, we're asked, assuming the same efficiency, would 377 grams of ethanol provide more or less or the same amount of energy? So to do this, we just set it up the exact same way and then compare our two numbers. 377 grams of ethanol over 1. Ethanol has a much lower molar mass of 46.07 grams per mole, but it also produces much less energy per mole. So we see that it only produces about 2,673 kilocalories in that weight of ethanol. So we compare these two numbers and we see that it produces quite a bit less energy than our 2-methylheptane. Our next problem is pretty similar. We have a hydrocarbon, cyclopentane, and we're combusting it. And the first thing it asks us to do is write out a balanced equation. So the first thing that I'm going to do is do that. I have my 2 C5H10 plus 15 O2 yields 10 CO2 plus 10 H2O. Obviously, I did that pretty fast. But really importantly, just to remember how to balance equations, we just remember that combustion reactions produce carbon dioxide and water, and they react with oxygen. And next, we're asked how much energy is released during the complete combustion of 431 grams of cyclopentane. Interestingly, I don't really need the balanced equation to do this, but we still wrote it just to get some balanced practice. So I have 431 grams of C5H10 in my sample, and I want to figure out how many moles that is. So 70.14 grams is equal to 1 mole, and 1 mole has a heat of combustion of 786.6 kilocalories. I'm told that earlier, which means when I combust 431 grams of cyclopentane, I release 4,830 kilocalories of energy. So be sure that in these problems, you're not really getting thrown off by the balanced equation. We don't need that to answer it. We only ever need balanced equations when we need to use a molar ratio. A lot of times people get that confused, so I'll repeat it. We only need balanced equations when we need to use a molar ratio. In this problem, we don't, so we are good. And then lastly, another similar type of problem. A combustion reaction is exothermic. It obviously releases a ton of energy. The heat of reaction for the combustion of cyclopropane is 499.8 kilocalories per mole. What is the heat of combustion for cyclopropane in kilocalories per gram? Let's do that one first. 499.8 kilocalories per mole. We want to turn it into kilocalories per gram. So we are going to divide it by the molar mass, which is 42 grams per mole. We get about 11.9 kilocalories per gram to plug in as our heat of combustion up there. Next, how much heat will be given off in molar if molar quantities of cyclopropane react to the following equation. So we're given a little we're given a little balanced equation over here, and we're already told that it releases 499.8 kilocalories per mole, and then in our balanced equation we see that we have 2 moles of it. So what do I need to do to solve this? I need to take 499.8 and multiply it by our 2 moles to get 999.6 kilocalories in this specific balanced equation. So I can call that kilocalories per reaction. Again, I think the most complicated types of these problems are the ones that involve stoichiometry, but hopefully with enough practice that the owls give you, all of these thermochem problems become pretty second nature to you. So feel free to watch through this video as you work through your owls, but make sure you get all of them done for good practice. And thanks, y'all, and enjoy your break.